AmberSemi's AC Direct DC enabler is a brand new topology, a new architecture that extracts DC power directly from AC mains, eliminating the need for standard conventional switch mode power supplies like what we're showing here on the left. Traditional switch mode power supplies need bridge rectification. They need big, bulky electrolytic capacitors that sit on the input that are going to have to deal with all of that input voltage that's coming in from the line. Amber's technology has found a way to extract DC power directly from AC mains and eliminate these big, bulky, limited reliability components, reducing the overall system size to get DC from AC by a third or even a sixth of traditional switch mode power supplies, and eliminating 2.5 times the amount of components. This overall not only reduces the system size, but it also increases the reliability of the system. With a wide input voltage range of 25 up to 277 VAC, and even the flexibility to go higher, or the output voltage that's able to be configured from 1.8 up to 24 volts, this device offers the maximum flexibility that's needed for a wide variety of system implementations. What we're demonstrating here is a discrete implementation of Amber's AC Direct DC enabler. This discrete implementation was to validate the performance of the device before it becomes integrated into that little IC that you see on top. Now, what we have here is our AC Direct DC enabler hooked up directly into the AC mains, 120 volts, 60 hertz. On the output, we have a power meter that's going to be evaluating voltage and current as we use these different types of loads in order to see how that voltage looks and what the current looks like in order to validate this performance. So what I'm going to go through is I'm going to show each one of these loads, and we can look at the power meter and see how it's performing. The first load is this disco light. You're looking at about 0.2 amps of current at 5 volts. So the maximum that this device is built to handle is 5 watts of power. So that is 1 amp at 5 volts. This is a fixed 5 volt output. The second load that I have is a fan that has multiple speeds. So this first level is looking at about 0.15 amps of current. As I scale it up into level 2, we get about 1/3 of an amp of current. And finally, level 3 is 2/3 of an amp of current. You can see even though that we're increasing the current to the load, the voltage stays very tight to that 5 volts. The third is a light that provides full range dimming. So right now this is at max and it's consuming about 0.64 amps. As I scale this down, we can see how that voltage still stays tight, even as it goes down to 0.1 amps. And finally, in order to see the device function at its absolute maximum power, we have a resistor inside of a box here. And as I turn this on, you'll see that we're consuming almost 1 amp of current, and we're at a very consistent voltage with what we've seen across all of these loads. So this discrete implementation was built in order to demonstrate and validate the performance, and now all of that is integrated inside of this IC. And we're going to have samples back within 2023. What we're looking at here is the first of multiple performance metrics that we're evaluating, not only for AmberSemi's AC Direct DC enabler, but also comparing against what's being used in the industry to date. The first one that we're going to be looking at is load transients, and this is at 120 volts. And what's happening here is we're stepping the load from 0 to maximum power for each one of these devices and evaluating how the voltage responds. In each one of these, the pink line represents that output load. And in company 1's case, it's about 0.75 watts of power. Company 2, 3, and 4, we're looking at about 2.5 to 3 watts of power. In Amber's case, we're looking at 5 watts of power that we're fluctuating from 0 to max. Now, the lines on top represent that output voltage. Are we able to get back to steady state regulation and output voltage in which the overall system best performs and what the load is really looking for from the power solution, power system? So in each one of these devices, you can see that there is no straight line of steady state regulation for any of them, 1, 2, 3, or 4. When you look at Amber, we immediately snap back to regulation. Each one of these load steps is at 1 millisecond, and within under 300 microseconds, we're able to get back to steady state 5 volts output. And this is very common in applications like switch activation or wireless radio transmissions, in which the load will fluctuate in how much power it needs. By staying above 4.7 volts and by staying below 5.2 volts, we're able to stay within that safe operating range and also get back to steady state 5 volt regulated power, which means that we are overall reducing noise within the system and increasing performance. Similarly to the previous slide in which we were looking at dynamic operation, what we're evaluating here is steady state operation. If I look in the top right, what we're evaluating is regulation of output voltage and evaluating how that performs as you increase power to the load. In company 1 through 3's case, you can see as current rises, voltage drops, which is traditional of switch mode power supplies. In Amber's case, we're able to stay flat. From 1/4 watt of power all the way out to 5 watts of power, we can give a consistent 5 volt output. Now in the top left output ripple, Amber is able to stay sub 50 millivolts peak to peak, versus each one of these other devices is more than 100 or even 200 millivolts peak to peak. Overall, that increases total noise within the system, decreasing performance. Finally, what we're evaluating on the bottom is efficiency. As you can see from Amber, the orange line, we're able to stay flat at almost 80% efficient from 1/2 watt of power all the way out to a maximum of 5 watts of power. In every other one of these devices, you can see that they're pretty flat around 70% efficiency, all the way out to their maximum output power, which is only about 3 watts of power. AmberSemi's AC Direct DC Enabler represents the best-in-class power system for any housekeeping power applications. With a wide input voltage range of 25 to 277 VAC, an output of 1.8 to 24 volts DC that's completely configurable, it is a global system solution for almost any residential, commercial, or industrial applications. For more information, please visit AmberSi.com.